And so what Chapter 15 does is, some of you may have already realized the fact that how is it possible to have these two processes that would be antagonistic to each other? How does this be controlled and regulated? Because otherwise it would be futile. If the moment you have the glucose and you break it down to pyruvate, if it then just goes from pyruvate to go back to form glucose, you would never be able to get enough energy for you to live. And so, therefore, you need to make sure that that there are ways to regulate this metabolic process when one of them will dominate over the other, or even spatially regulate it, where some organs may be undergoing gluconeogenesis while glycolysis is happening elsewhere. Okay.
Is that a pear?
Pardon?
Is that a pear?
Yes. Yes, it's a pear. You know, it looks really smurfy in here because of the projector. But yes. No, I think whenever I made these, I just Googled, like, metabolism or something like that. That was one of the Google images that came up. Nice little pear with a little waistline thing. Okay. Shall we begin? So, what are some of the reasons why we need to be able to control this? Just give some examples. I gave, one example. But why? Why else? Why do you need to control glycolysis?
Like in case of famine or something, so your body is able to know like when it needs to make more, or when it needs to be active as opposed to.
Okay, right, during that, or even it doesn't have to be during famine. What's one time everybody has to go through this? When do we have to worry about it? Glycolysis versus gluconeogenesis.
When we're sleeping?
When you're sleeping, in between meals, right, there are just times that you cannot continually be undergoing glycolysis for all of your tissues, right? Because even just between meals, we would deplete our glycogen. So there are multiple reasons. That was just for glycolysis. You can think about with gluconeogenesis, the pentose phosphate pathway, things like that. So I really like this figure here. Unfortunately, it doesn't show up very well on the projector, but I really like it because it shows you how these all interplay. This is carbohydrate metabolism, so that would be the glycolysis and gluconeogenesis, how it leads down here. What would be this circle right here? That's the Krebs cycle, part of energy metabolism. But you can see how it also is related to the glycan biosynthesis, nucleotide metabolism. Of course, we already talked about the pentose phosphate. I mean, they're all just interrelated, and we're going to go into greater details both with amino acid and lipids later on in the semester. And so we have to be able to manipulate these so that way one is not scavenging at the cost of another metabolic pathway. Okay, so there are certain things that you should have known already from biology, in biology classes, cell biology and things like that. There's homeostasis, flux, and cellular differentiation. So what is homeostasis? Right, it's maintaining sort of like a biological equilibrium. Okay, versus flux.
Things are not in balance.
Well, it actually has to do really just with the movement, right? Movement from one process to another process. And then cellular differentiation. What does that mean? Okay, from your stem cells to what? Right. I mean, your hepatocyte, which is where are the hepatocytes?
Liver.
The liver, versus, they look very, very different, even morphologically than, say, like some of your neurons. Right? So you have to be able to differentiate, and they're going to have different processes that these have to all be able to do and to encounter. All right. So now we have to start to discuss some of the basic methods of metabolic control. And there are 4 major classes of these. And I do expect you to know what these are and also be able to give specific examples. Especially by the end of the semester, you'll be able to give lots of different examples of this. So these are the control mechanisms. Got the big boxes on them. So we have allosteric, covalent, substrate cycling, and genetic. That construction sound is really annoying. It's going to be around with us now for a long, long time to come. Okay. So, what do you suppose, what is allosteric? Pardon? A change? Could be. Well, you can have cooperativity. Is it always cooperative? Well, it depends. That's kind of because cooperativity doesn't have to be positive. You can have negative cooperativity, right? What's an example of negative cooperativity? Like an inhibitor, but what? What?
She's the children.
But what's just what type of inhibitor inhibition? Like there's one that we'll see a lot of that we've actually already encountered a time or two. Right, that's saying it's called feedback inhibition, where you have a further metabolite downstream or product from downstream that comes back and inhibits an earlier enzyme. Okay, and so allostery can be both positive or negative with respect to that. There we go. So these are effectors. We talked a little bit about that last semester. They can either be inhibitors or activators in that sense. But their binding affects the outcome of that metabolic pathway. I'm wondering how this will let me to see if it'll let me. So I'm just going to try something out real quick. So feedback inhibition. I don't have. So feedback inhibition being an example of an allosteric. Oh yeah, it does show up there. It's a different color. Okay, it's just an example of an allosteric interaction. And one example for that was like the ATP with the PFK in glycolysis. Let's see. Oh. All right, and so what about covalent modifications? What would that be? Phosphorylation is a big one, right? Because what happens when we say phosphorylation? And once again, it can either be positive or negative. It can be activating or inactivating, inhibiting. So phosphorylation is one way to do covalent modification. What's another way to do covalent modification? So just adding phosphate groups, what else could you add? Methylation, acetylation, when adding acetyl groups. There's glycosylation, they can add sugars to various things. But this is where you form a covalent interaction. There's a covalent bond that's affecting the output of the metabolic pathway. Okay. So this is going to depend on making or breaking a covalent bond. And like I said, the one that we're going to encounter the most is phosphorylation versus dephosphorylation. And it can be either inhibiting or activating. The third class, substrate cycles or substrate cycling, is, I think, the most nebulous of the four. To me, it was the most difficult to remember and to explain. What do you suppose that means? In a way, we actually have a couple of other examples that are even easier to explain. So this actually happens when you've got common metabolites in the metabolic pathways, but they use different enzymes, or maybe even multiple different steps, in order to do the reverse reactions. Okay? So you have these two opposing ones that are used by different enzymes or different steps. And you can activate or inhibit them separately. So what's one example that we've seen so far? Glycolysis and gluconeogenesis. And so in particular, in glycolysis, on step 10, we have pyruvate kinase. How does gluconeogenesis go backwards? Pyruvate. There's pyruvate carboxylase and this is two-stepper. And pep-carboxykinase, phosphoenolpyruvate carboxykinase. I'm going to write it all out. Okay, and so they each have their differences with the way that they are either activated or inhibited. Okay. Whereas if you just pick one of the ones that's not, it's like triphosphate isomerase, you can't use that. They really are. I mean, that's the same enzyme doing the same reaction both frontwards and backwards.
I have a question about that. So, for like glycolysis, obviously you want it to go in one direction. So, I'm guessing the cell has some way of forcing it to go forward.
Well, I mean, that's even just from basic general chemistry. What?
Like high concentration, low concentration.
Right. What is called? No. What is that?
Diffusion?
Pardon?
Diffusion?
Well, it could be diffusion, but just even in more broad terms of thermodynamic terms, what is it? Equilibrium, right? It's going to depend upon the equilibrium constant, and then that K versus the Q, the equilibrium coefficient at that time, or the reaction coefficient at that time. And so that's why it doesn't have to have more of one than the other, as it just has to be perturbed from its equilibrium. Okay, but it's not a really good way to regulate it, because if you just keep on making the stuff from up above, then it's going to keep on going forward. So it's just those are not a checkpoint. It says, okay, I see, a DHAP coming my way, and I need more glyceraldehyde 3-phosphate, or vice versa. Okay. And then there's genetic control, which is one that's fairly simple to explain. Maybe not as easy as covalent modification is pretty. But I mean, what about just controlling it genetically? What does that mean in simplest terms? How does that control a metabolic pathway? Right. Just don't make that enzyme, or don't make very much of that enzyme, and that metabolic pathway won't work. Or make a lot more of that enzyme, and that metabolic pathway would be activated. So that's a transcriptional control. Okay. So the amount of that enzyme is going to depend upon how much protein was made, which comes from transcription. Well, the protein technically comes directly from translation, but you get the idea. Translation can occur, transcription doesn't occur. Okay. And as I mentioned, you could already, if you think about it, see how some of these, maybe not genetic control, but see how we've seen some of these already at play with respect to glycolysis and gluconeogenesis. All right. And so we've already been answering some of these questions, but this is stuff to keep in your mind as we go along. And not only this chapter, but also in future chapters where they won't separate and have a different chapter on each one's, regulatory control. But you have to realize, are these futile cycles? And the answer would be no, because if it was a futile cycle, then we would die. Okay. They do compete against each other. And, wouldn't they just be unproductive, or, why don't they just lose their energy due to heat? Because we are not an isothermic, entity. We do heat that is given off, and so that's why the way that they're regulated is just a good example of using the various control mechanisms. Okay, so we're going to actually start off with hexokinase, and this is one that I actually have mentioned before. Okay, and I really wish that this would let me put in a blank spot, but I don't believe that this program will. Okay, so we have hexokinase. So as I mentioned before, there are at least 4 different isoforms, or isozymes, of hexokinase. And they're numbered 1 through 4. They use Roman numerals. The hepatic isoform of it is called hexokinase 4. It's also commonly referred to as glucokinase. And that's one of the reasons why this is one time where if you say glucokinase, it has a very specific meaning. That's the form of this enzyme that's in the liver. Okay, whereas muscles and other tissues typically have hexokinases 1 through 3. And so that's why here you have to be careful. You can't just call all them glucokinases because it's the one that's for the liver. But in particular, hexokinase 4, or also known as glucokinase, it has a much lower affinity for glucose. What is glucose with respect to hexokinase? Is that the reactant or is that the product? It's the reactant because hexokinase goes from glucose to glucose 6-phosphate. And then in gluconeogenesis, as it mentions down below, the idea is that glucose 6-phosphatase is the enzyme that does the reversal. Okay, and so why is it important that the form of this enzyme in the liver has a lower affinity for its substrate? So this is where you're going to have to go back to this idea of, here, let me see if, that's a good way to answer. Let's see if I can write. I do not know if it's going to, well, we'll find out if this will let me go back to the PowerPoint. But this goes back to the idea of Michaelis Menten. So if we assume, which this one's allosteric, so it's not, doesn't follow the traditional Michaelis Menten kinetics, but whenever we say apparent affinity is lower, so we're just looking at the rate of the reaction as a function of, here it's glucose, but I'm just going to put substrate. Okay? In an ideal Michaelis Menten, it would look something like this, right? Because at some point in time, you're going to bottom out. I shouldn't say it's not bottom out. It flattens out. Bottom is a really bad choice of words there. But it... Oh, I can do this one. It just won't let me draw on there. And so remember, that was your Vmax. Because at some point in time, you've got you can't add any more substrate. Because the fact is that it is fully saturated. All the enzymes that are possible all have bound substrates. Okay. And so because of that, then you can find the Km. See in this color. And so roughly the Km, we go about half of Vmax, you go down. So there would be the Km right here. However, for the liver form of this enzyme, if it has a lower affinity, or apparent affinity, what do you suppose the liver form is going to look like with respect to its Km? Is it going to be a smaller Km or a bigger Km? It's a bigger Km, okay? And so let me get a different color. So perhaps it looks something more like this. Whoops. And I'm not saying that this is... Oh, the colors are really different. On my computer, that's green. Red and green. So I apologize that the Smurfy projector is changing all the colors. And I'm not implying here that the liver enzyme has a higher Vmax. This is just an example of something that would have a weaker affinity, and it's allosteric. How do we know that this is allosteric? It's sigmoidal, okay? And so that's sigmoidal. Remember, that was just a giveaway that it was allosteric. You can still get an apparent Vmax. Let me see. I'll use the little highlighter. Now, this is supposed to be green on mine, but you go over. Whoops, I didn't do a very good job drawing straight with my finger. You go down, but this would be where the enzyme, apparent Km for the liver enzyme would be, or in this example. That is really not green. Okay. But this is to show you what I mean by the fact that it has a lower affinity for its substrate. Why is that important? That liver has first choice of what?
Like the nutrients. So there's an abundance. So if it digests it quickly, or broke down quickly, then there would be none left in the muscles.
So I like some of your rationale, but it's just worded a little oddly. So maybe let's start with the second part of that question. What cells or tissues require glucose the most? Muscle, but what else?
Brain.
The brain. That's number one, first and foremost. Without the brain, nothing else would happen. And so, and it has to have glucose. And so, you do not want the liver to compete with those. And so, it's not so much that it gets it first, as in what we'll talk about in a moment, is the fact that it's really sensitive to the blood glucose level. Okay, and so you have to have a much higher concentration of glucose in your blood before hexokinase 4 kicks in and starts doing glycolysis for the liver. Because if you're below that concentration, it says, okay, I'm anthropomorphizing, which I had one of my professors hated when I did that. But the liver's saying, hey, it's below my Km, and so therefore the other tissues are going to need it first. So hexokinases 1 through 3, those forms 1 through 3 will have a much tighter, much lower Km, so that way they can bind the glucose, use glucose for glycolysis and get the energy from it, and the liver will wait its turn. Okay. And so, what primarily happens that's one reason. What primarily happens in the liver that doesn't happen in other tissues?
Stores glycogen.
It stores glycogen, so glycogen synthesis, and what else? Well, muscles also can store some glycogen, but there's something else really important that it does that we've actually been talking about already. Gluconeogenesis. And so its isoform, if it had a really, really low Km, not only would it be stealing the sugar from other tissues, but it would be competing with its own glycogen synthesis and storage. Okay, and so that way it would just be using it up. The moment you try to make the glycogen or just store it, it'll just be kicking it back. So that's why you don't want a fetal cycle in the liver itself, within the actual hepatocyte, but we also don't want it to compete with the brain and the muscles and the heart and things like that needs more energy. Okay, and then finally, both hexokinase 4 and its antagonistic enzyme or counterpart in gluconeogenesis are transcriptionally regulated. You just don't make as much hexokinase 4, then you're not going. The liver, because it's hexokinase 4, the liver itself won't undergo glycolysis as readily as it would gluconeogenesis, and vice versa. It's just that transcriptional regulation typically is a little bit more longer term than something that you just downed that big Hershey bar, which please don't do that. But you downed it in 30 seconds, and it would take too long for the transcriptional control to kick in for you to. If that was the only way that was regulated.
Happy Valentine's Day.
Yes. So yeah, I had one of my brothers that would just freak me out, and I know he's if he's not already pre-diabetic, he's going to end up being diabetic. So first of all, being Native American, but secondly, we have a much higher incidence rates of diabetes. But secondly, for example, whenever he and my mom flew down to visit me one time, and I went to take them to the airport, and on the way there, we had stopped and we ate, and still have a couple minutes, but we stopped and we ate. And when we stopped to eat, he had, is that the Golden Corral, not my choice, but their choice. And, he has ice cream and everything there, and it's the Golden Corral on the north side of town. And, it's next door. It's really close to Steak and Shake. And so we were just going to go, it was happy hour. We were going to go to Steak and Shake to get our half-price sodas on the way to the Tampa airport. And when we got the order, Michael also ordered a large shake. Like, you just literally just ate. And then anyone here who knows where the Steak and Shake is, it's right there by the interstate. I mean, it's right adjacent to the interstate. He had that thing completely drank from the drive-through window to the time that we got to the interstate. Like, it just blew my mind.
How do you not get brain freeze?
Well, he has to have a brain first, but yes, that's why I'm going to say that he just, it's amazing. Yeah. So, yeah, he's not that good. Yeah, for a diabetic study, I'm sure that he is. So, okay.
Eat more fruit.